Hi, this is Group 3. We're presenting Assignment 4 for Material Science. So question 1 of Assignment 4 asked us to look at the electron configurations for our metals and our semiconductor. Our first metal was copper, which has 29 electrons. So its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Our second metal was palladium. The electron configuration for palladium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d8. And then our semiconductor was aluminum nitride, which has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. And then below each of those, it kind of shows the picture for the electron configurations. Question number 2 for assignment 4 asked us to look at the band gap of our semiconductor. Again, our semiconductor was aluminum nitride. So what is a band gap? So when separate atoms in one solid come in close proximity of another atom, it causes one atom's electrons to act upon adjacent atoms' electrons in their nuclei. Um, and when they come into close proximity and they act on each other, it influences the atom's electrons to split into closely packed electron states called electron energy bands. And then the small spaces between the bands are called band gaps. If you look at the picture on the right, it kind of shows what this means. And then we found that aluminum nitride's band gap is 6.2 eV.
Alright, question 3 asked us as to what element was best for p-type doping of aluminum nitride and aluminum gallium nitride. So firstly, what is p-type doping? P-type doping is when there's an excess of holes in the semiconductor, which holes are important because it helps transmit the electrons faster throughout the semiconductor, so it's better for more electron conduction. So firstly, for aluminum nitride, beryllium was best for p-type doping because it has less valence electrons than aluminum and nitrogen atoms, so that empty space in the electron configuration opens up an extra hole, and then it creates more holes in the lattice, and holes are positive. P-type doping for aluminum gallium nitride was found to be magnesium for the same reasons. And then for N-type doping is the fairly same procedure, except it's opposite, where N is an excess of electrons rather than holes. So for both aluminum nitride and aluminum gallium nitride, it came out to be silicon is best for N-type doping because there's more valence electrons than aluminum and nitrogen atoms. That extra electron in the semiconductor lattice helps conduct electrons better, and electrons are negative.
For question 4, we were asked what are the mobilities, concentrations, and electrical conductivities of free electrons and free holes, respectively, for our intrinsic semiconductors. To get the answers for our semiconductors, which were aluminum nitride and aluminum gallium nitride, we were able to use the equations on the right to calculate the electron mobility, the hole mobility, the electron concentration, the hole concentration, and the electrical conductivity. To get the electron mobility for aluminum nitride, we used the first equation, which was able to give us 100 centimeters squared per volt times second. Using the second equation, we were able to gain the hole mobility, which was 10 centimeters squared per volt second. Using the third equation, we were able to get the electron concentration, which was 10 to the 8 centimeters cubed. To get the hole concentration, we were able to use the fourth equation on the right, which gave us the same answer, 10 to the 8th centimeters cubed. And to get the electrical conductivity, we were able to use the last equation on the right, which gave us 10 to the negative 12th Siemens per centimeter, which is very low. We were able to do the same for aluminum gallium nitride, which, when using the equations on the right, our electron mobility was 1,000 centimeters squared per volt second. Our hole mobility was 100 centimeters squared per volt second. Our electron concentration was 10 to the 8th centimeters cubed. Our hole concentration was the same, 10 to the 8th centimeters cubed. And our electrical conductivity was also 10 to the negative 12th Siemens per centimeter, which is very low.
Alright, question 5 asked for the fun stuff, the applications of our semiconductors. It asked for applications on 3 aspects of electronics, LEDs, and photovoltaics. So firstly, for our first material, aluminum nitride, ALN, for electronics, it's used in heat sinks and heat spreaders for excellent thermal conductivity, meaning that it dissipates heat very fast. Radio frequency absorbers, so it's used in most radios, like the radio in your car uses aluminum nitride to absorb the radio waves out of the air. For LEDs, it's applied in producing UV radiation waves, so definitely useful for disinfectants and imaging, especially in the medical field. Things need to be disinfected, and it's always not easy to wipe stuff down with disinfectant wipes. Usually it's easier to use UV radiation waves to kill bacteria. And for photovoltaics, since aluminum nitride works with UV radiation, it's useful for absorbing UV light out of the air from solar panels, from the sun into solar panels. And for applications of our second semiconductor, aluminum gallium nitride, AlGaN, in electronics, it's used for radio frequency wave absorbers again, so previously, like aluminum nitride, it works as the same function in radios and such, where it can absorb radio waves out of the air. And then for high electron transistors, it's also used in. And then LEDs, it's applied in producing UV radiation waves, so it can be mixed with other elements too to produce colored LEDs. And then photovoltaics, it's used in photodetectors, which can detect light but not UV radiation as well.